Hello and welcome to this demonstration in the course for Secure Systems Engineering. In this particular demonstration, we will look at covert channels. So we've already seen the theory about covert channels and how they can be established through the cache. And in this demonstration, we'll actually look at creating such a covert channel and how we could actually transfer information from one process to another. So this particular setup may not be runnable from the virtual machine, although we will actually provide the source codes that can be downloaded and tried on your own machines. So while setting up a covert channel using the cache memory, the first thing to identify when we are actually starting to design a cache based covert channel is to identify information about the processor and also about the cache memory present in that processor. So the machine that we are using over here is a regular i7 machine from Intel, and it is running an Ubuntu operating system. The first thing to note is details about this processor. So this processor is a 4-core processor, and these 4 cores there are 8 hyperthreads. Essentially, per core has 2 hyperthreads. If you want to try this on your own system which is running Ubuntu, you can run the command /cat/proc CPU info, and it would list details of all the processors present in your system. For example, over here, since we've mentioned that this is a 4-core machine, so each core is given a particular core ID starting from 0, 1, 2 and 3. So the core ID, for example, over here is 3, and as we scroll upwards, we see other core IDs of 1 and 0 and so on. The next thing we also mentioned that in this processor we had 2 hyperthreads sharing the same CPU core. Particularly, what we see if we scroll up is that the processor number 0 and the processor number 4 share the same CPU core. So we can verify this as follows. So this is processor 0, and which is present in this on the core with an ID of 0. Now if you look at the processor 4, so processor 4 is also on the same core with the same core ID. Similarly, if you go through the other things on this particular machine, you would see that processor 1 and processor 5 are sharing the same core, essentially the core ID 1 and so on. In order to create a covert channel between 2 processes, what we would require is to identify 2 hyperthreads which are running on the same core. So let us choose the cores processor 0 and processor 4. The next thing we need to know is the cache structure for this particular processors. So this information can be obtained from the directory sys devices. CPU 0 cache. So this particular directory lists all the cache memories that are accessible from the CPU 0. So we'll go into index 0 and we'll look at the type of cache which is present over here, and the type is D, data, so which indicates that this particular cache represented at CPU 0 index 0 is a data cache. It has a size of 32 kilobytes as seen over here, and we can also get the information about the other processors which are sharing this particular cache memory. So this can be obtained from the file shared CPU list, and we see that there are 2 processors, processor 0 and processor 4, which are actually sharing this particular cache. So now if we want to build a cache covert channel, we could have and we want to build this cache covered channel between two processes and share information between these two processes. What we would be able to do is we could run one process in the CPU 0 and one process in CPU 4 and make use of the shared cache to exchange information. We can also obtain other details about this particular cache memory. For example, the ways of associativity is as follows. So, this is a 8-way associative cache, and the number of sets that are present is 64. Okay, and the size of each cache line that is present is as follows, is also 64. Based on all of this information, we can next construct a typical address of such a cache. So, what we did mention was that this particular cache memory had a cache line size of 64 bytes, which would indicate that the lowest bits of the address, the lowest 6 bits of the address comprises addressing within the cache line size, which is of 6 bits. It also had 64 cache sets, and therefore, in order to address 64 cache sets, we need another 6 bits, and therefore, we have set addressing which has like another 6 bits. These two actually give the offset within a line, and these 6 bits provide the address for a particular set. So, later on we would as we would see in the programs, we would require to know such information in order to build our cache based covered channel. So, now that we know that about the cache structure and the processors within this particular machine, let's next try to find out how we could actually build a cache based covered channel. So, what we want to achieve is that we have two processes running on the system. These processes are called sender and receiver. And receiver. And we assume that these two processes are completely isolated from each other. You could think of a sender to be a privileged process, like something like which is run by the system administrator, and the receiver process to be something which is an unprivileged process. So, you can also assume that these two sender and receiver processes are run by totally different users. So, what we do know about the operating system and the hardware is that there are various mechanisms which are incorporated in both the hardware and the system software that would ensure that this receiver would not directly be able to read or write data from the sender and vice versa. However, what we will show now is that the sender and receiver can actually use a shared cache memory to transfer information from one process to another. So, note that when a cache memory is used, there is no implicit way to actually for one process to read from the cache memory, but what we will see, and as we have seen in the theory videos before, we could use the execution time for a memory access to pass on information from one process to the other. So, let us say that we have a message and we assume a binary message of say 11011101 to be sent from the sender to the receiver. What we assume further is that both of these processes, that is the sender and the receiver, are sharing a common cache memory and are running on that on the same processor. For example, the processor 0 and processor 4. So, what is done in order to create the cache covered channel is that the sender and the receiver first agree upon a specific set of ports. So, let us call these ports as 10, 20, 30 and 40. So, we call two of these ports as the data ports. So, let us call data ports as and 30 and 40 as the control ports. So these ports are prior to actually starting the Covert channel. The sender and receiver agree upon these ports, and essentially in our program, the demonstration that we would see, we would use one port, say port 30, to send the odd bits, and port 40 to send the even bits. So for example, in this particular case, we would have these ports sending the port number 10. So since we start with the 0th bit, this particular bit, this thing would be actually sent to through this 1, and the next bit which is 1 again would be sent on this port 10. The third bit, which is 0, would be sent here with the control line even, and the fourth bit, which is here, would be having the control of 30 and sent on this port 10. So in this way, what would happen is that we are sending bit by bit from the sender to the receiver. So let us see how this program actually works. So over here we have two completely different programs. One is known as the receiver.c, the other one is the sender.c, and we will also be sharing these programs with you, so you can actually try this out on your machines. So the first thing we do is do a make clean and make, and we obtain two executables. One is the sender and the second is the receiver. So what we will show is that it is possible to actually communicate information from the sender through the receiver through the shared cache. So before going into details about how this program is actually working, we'll just look at the demonstration first. The first thing to do is to start the receiver, and we need to ensure that the cache is shared. And as we've seen earlier in this video, the processor 0 and the processor 4 are essentially sharing the same CPU core. Thus, we need to ensure that both these processes, the receiver and the server, are executing on exactly this core. So we can do this by the task set command, task set -c 0 /receiver, and we provide it the agreed upon ports over here. So this 10, 20, 30, 40. So recollect that we define the ports in the cache Covert channel as essentially the different cache sets. So there were 64 cache sets in our L1 data cache, and we have decided to choose these 4 cache sets, cache set 10, 20, 30 and 40, for our communication. 2 of these cache sets, 10 and 20, are used for transferring data, while the cache sets 30 and 40 are used for control. So let's start the receiver, and in a totally isolated environment, we start the server as follows. So we need to ensure that the server is running on the CPU 4. So we run the task set, specify the CPU that we want to run. In this case it is 4, with exactly the same agreed upon ports 10, 20, 30 and 40. So what's happening now is that the sender is beginning to send a 0th bit. It's at an even location, and we see that this sender is essentially through the cache able to communicate to the receiver. So currently this particular 0 bit has been received over here by the receiver. So the next bit which is sent by the sender is 1, so this is the odd bit, and we see that the receiver has received this particular bit. So let's look for some more time to see more bits being transmitted. The third bit being sent is 1 again, so this is an even bit, and we will see that after some time the receiver has indeed received this bit as well. See, the bit number 2 is the even bit, got a value of 1. So we could just wait for maybe a minute or so to see more bits being transmitted. So this is an extremely slow process, but what it signifies is that these two processes, sender and receiver, in spite of the heavy protection provided by the operating system and the hardware, have been able to actually communicate with each other. So this was on two regular processes, but we could also demonstrate this on various other infrastructures. For example, even with the trusted execution environments such as the SGX and trust zone that we have studied earlier in these lectures, such kind of covert channels can be done from a trusted environment to the untrusted environment. So one thing that demarcates a particular covert channel is the rate at which data can be transferred from the sender to the receiver. So over here, as we see, it is an extremely slow process. So typically the units would be something like bits per second, and as we see over here, this code is not very optimized. This seems to be much lesser than 1 bit per second, but nevertheless we see that attackers are quite motivated, and the rate of transmission is not a very critical issue for attackers as long as the information can be obtained on the other side. Now that we've seen how these programs work, so let's look a little more in detail about what is happening inside this program. So let us stop the receiver and the server. Now one thing for you to think about is that recollect that or if you just go back on the video, you would see that there are some bits that get received even though the sender had not yet started. So one thing for you to think about is why such a thing has actually happened. Okay, so let's go into the code. We will open our editor and look at the sender code first. Okay, so this code has been written by Gnanambika, who is a PhD student at IIT Madras. So important things over here is this particular time period, and we will refer to this later on in this particular code. And what we see is that various attributes about the cache memory present in the system, at least the cache memory that has been targeted for this covert channel, has been hash defined over here. For example, the decache size of 32 kilobytes, number of set bits, which is 6 over here because we have 64 different sets. The offset bits within a cache line is again 6 bits because each cache line is of 64 bits. And something known as total bits, which represents the associated bits, set bits and block address bits. One thing what was important over here was that the associativity of the cache memory. So recollect that this particular memory was an 8-way associative cache, and therefore in order to create a conflict with the particular set, there should be 8 addresses falling on that same cache set. The 8 addresses would should be designed in such a way, or should be crafted in such a way, such that each of them fills a particular way in a cache corresponding to that set. So the arguments that we provided over here, that is the ports, the control ports and the data ports, that is 10, 20, 30 and 40, are taken from the command line and set into these various integers, set index A0, A1, B0 and B1. So A0 and A1 are used to transfer 0 and 1, while B0 and BE are used for the control ports, and where they are used to transfer the odd bits and the even bits respectively. The next thing we do is we craft different addresses. Note that we require 4 sets of addresses. Each is a collection of 8 different addresses. So this, for example, A00 to A07 is an 8-way, corresponds to the 8-way associative cache. So I will not go into details about this, but given the fact that what we have discussed earlier in this video, you can see how the 8 addresses are crafted so that all of them would access exactly the same set. We assume policies such as the least recently used to be implemented in the cache, and assume the fact that all of these 8 addresses would fall in the same cache sets, but in different ways of the cache. So similarly, we have A0, A1 addresses being crafted, B0 addresses, and the BE addresses being crafted. The next thing would be quite interesting. So we would look at how the data is being transmitted. We have defined the data to be transmitted from the sender to the receiver as follows. So the data comprises of this binary bits 0, 1, 1 and so on. And what we do over here is that we start to craft memory access and start to actually send them from the sender to the receiver. So important in this particular thing is this particular for loop. So each iteration is done for epoch times the time period. This is to ensure that the receiver, which is running asynchronously from the sender process, has sufficient amount of time to actually read this information. So we look at how the epoch is defined, which is hash defined to 128 over here as seen over here, and the time period is 2 power 24, which means that these loops are run for a total of 2 power 24 times 128 things. So this would be long enough to give the receiver sufficient amount of time to actually detect bits being transmitted. The next thing we do is create memory accesses to various locations. Now TA_0 and TB_0 correspond to load and store operations to these addresses corresponding to the data being transmitted. Recollect that TBs are used in order to control the data and specify odd or even bits being transmitted, and TAs are used to send zeros and ones respectively. So essentially this is the communication which is happening by the sender. The sender is making memory accesses to these particular memory addresses. So each time the sender actually makes such a memory access, the data, if it is not present in the cache, would be fetched from a lower cache, in this case the L2 or L3 cache, and stored in the L1 cache as well as stored in a register pointed to by this. Now what happens on the receiver side is that the receiver also runs a similar loop as shown over here, but the receiver would also time that particular loop. Now due to the conflicts that arise due to the common cache and the agreed upon cache sets, the conflicts may actually cause certain memory accesses to be faster and certain memory accesses to be slower. So the increased time would indicate that there is something being transmitted by the sender on that particular cache set, and therefore a miss has occurred. The data has to be retrieved from the lower cache or from the DRAM. Thank you.